All right, in this video we're going to be looking at section 4.3, and that's going to be partial derivatives. And we have partial derivatives if z is equal to f of x comma y, then the partial derivatives of f, if they exist with respect to x and y, are as follows. dz dx is equal to df dx. And then we use a delta instead of a d, but we still write it. We might say partial of z with respect to x, or partial of f with respect to x. Sometimes it's read d, z, dx, etc. is equal to f, and then we have the subscript x. That's for the first partial with respect to x. If x comma y is equal to the limit, as delta x goes to 0, of f of x plus delta x comma y minus f of xy all over delta x. That's your partial derivative of f with respect to y. The partial of z with respect to y is equal to the partial of f with respect to y is equal to f, and then subscript y for derivative with respect to y of xy. That's going to be the limit as delta y goes to 0 of x comma y plus delta y minus f of xy all over delta y. That's the partial derivative of f with respect to y. Partial derivative notation of x at a point, for example. So partial derivative of x evaluated at point a comma b on the graph of z is equal to x, z is equal to f of xy. So partial of z with respect to x evaluated at ab is going to be f subscript x, so partial of f with respect to x of ab. So we're going to do some examples of finding some partial derivatives. So example 1, find the partial derivative with respect to x, partial derivative with respect to y for the function z is equal to f of xy. And when we do this, if we're taking derivative with respect to x, the y is treated as a constant, and then if we're taking the derivative with respect to y, then the x is treated as a constant. So when we take the partial derivative with respect to z, the cosine of 3y is just a constant factor. It's just going to be there. So really what we're going to be focusing on is taking the derivative of the sine of 3x, which is going to be 3 cosine of 3x by the chain rule. And then we just have the factor of cosine of 3y just attached to it. We don't do anything with it. It's a constant. Okay. Now if we take the partial of z with respect to y, now the sine of 3x is treated as a constant, and we're going to take the derivative of the cosine of 3y with respect to y. So you're going to get a negative 3 from the chain rule, and derivative of cosine is minus sine, so that's where the minus 3 and then sine of 3y comes from. We'll slide the factor of negative 3 out, and so we'll have negative 3 sine of 3x and sine of 3y. All right, let's go on to the next example. So we have z is equal to 1/2 sine of 2x minus y. We're gonna find a partial derivative with respect to z, and we're gonna evaluate it at the point pi over 2 comma pi over 3, and then we're gonna find the partial derivative with respect to y and evaluate that at pi over 2 comma pi over 4. Okay, so we're going to find the partial derivative with respect to x. Okay, so the y is treated as a constant, so that'd be 1/2. And then chain rule, sine of 2x minus y. So when we take the derivative of that, that would be the cosine of 2x minus y. And then by the chain rule, that'd be times 2. And then derivative of y with respect to x would be 0. And so that's where the 2 cosine of 2x minus y is going to come from. Okay, and so our partial derivative with respect to x is going to be cosine of 2x minus y. And then we'll evaluate that at pi over 2 comma pi over 3. So that's going to be the cosine of 2 times pi over 2 minus pi over 3. Okay, so it's going to be cosine of pi minus pi over 3, which would be the cosine of 2 pi over 3. And cosine of 2 pi over 3 is going to be negative 1/2. And so that is going to be a slope of a tangent line, and we'll kind of go off on a tangent here. And we'll also find the point of tangency. So we're going to find the point on the graph. So z is equal to 1/2 sine of 2 times pi over 2 minus pi over 3. So that's going to be 1/2 sine of 2 pi over 3. And sine of 2 pi over 3 is root 3 over 2, times a half would be root 3 over 4. And so that gives us the ordered triplet, pi over 2, pi over 3, and root 3 over 4. Okay. If I wanted to kind of come up with, it's not quite the equation of the tangent line, it would be an equation of a tangent plane. We do z minus z1 is equal to mx minus x1. So z minus root 3 over 4. The slope is going to be what we found the partial derivative with respect to x was, evaluated at pi over 2 comma pi over 3, which was minus 1/2. And then x minus pi over 2. And so if you graph this, this would give you a tangent plane. So z is equal to negative 1/2 x plus pi plus root 3 all over 4. Okay, so that'd give us a tangent plane at that particular point, and that would contain the tangent line. So plane containing the tangent line. All right. Now, if we want to actually come up with the tangent line, what we want to do is we're going to parameterize here, and so we're going to let x equal t, and z is going to be the slope of negative 1/2 t, and so I'm coming up with a parameterization. Now, when I actually do it in my tangent line, I'm going to do t plus, and then where we want it to be is at pi over 2. Okay, we're not going to do anything with y. This is going to be parallel with the x-axis. Okay, and so the y will be just pi over 3, and then we have the slope, negative 1/2 times t, and then where we want it to be at root 3 over 4. And if we go to the next slide, we'll see that. So let's go to the next slide here. And so here's the point here, and then our tangent line. Okay, and so it does have a slope of negative 1/2, and that's if we're looking in the direction of. So if we're going to walk parallel with the x-axis, we're going to go downhill. Okay, all right. Let's go back and rewind. Okay, so that's our tangent line. Now we're going to find the partial derivative with respect to y. And so when we take the derivative, it's going to be 1/2 cosine of 2x minus y. And then by the chain rule, the x is treated as a constant, so this would just be 0 minus 1. And so that'll end up giving us a negative 1/2 cosine of 2xy. 2x minus y. Okay. So 2, and then we're going to have the cosine of 2x minus y, and then a negative by the chain rule. So if we evaluate our partial derivative with respect to y at the point pi over 2 comma pi over 4, that's going to give us a slope of a tangent line in the direction of the y-axis. So we're going to go ahead and plug that point in. And so we're going to be finding negative 1/2 cosine of 2 pi over 3, and cosine of 2 pi over 3, no, that was the last one. Sorry, our point changed. So it's pi over 2 comma pi over 4. So we're going to have pi minus pi over 4, which will be 3 pi over 4 inside the cosine, and the cosine of 3 pi over 4 is negative root 2 over 2 times the negative 1/2 will make that a positive root 2 over 4. Okay, so let's make that correction here. So this should be a positive. Okay. All right, so if we want to find the point on the graph, so we got the x is pi over 2 and the y is pi over 4. If we want to find the z coordinate, it's going to be 2 times so it's going to be 1/2 sine of 2 times pi over 2 minus pi over 4. So it's going to be 1/2 cosine of 3 pi over 4. And so that's going to be equal to root 2 over 2, which is the sine of 3 pi over 4, times the 1/2 gives us the root 2 over 4. And so the ordered pair, ordered triplet we'd have there is pi over 2, comma pi over 4, comma root 2 over 4. Okay. So again, if we want to find like the plane containing the tangent line, it would be z minus root 2 over 4, and then our slope, which should be a positive. Okay. All right. So z is going to be equal to, again, missing the, put a negative on there on accident, plus, that would be a negative here. Okay, so that'd be our plane containing the tangent line. So then our tangent line would be pi over 2, comma t plus pi over 4. So we want it to run along the y-axis. And then root 2 over 4, and then it should be a plus, a positive slope here. Okay, so let's go ahead and look at this point here, and that'll be on the next slide here. So we can go on to the next one. Okay, so here's our point, and our slope was positive. So is this graph correct? Let me double check this graph. I might have something in error. No, it's fine. It's just the perspective looks like it's not parallel. So down here, looks like they're a little bit more parallel, and so this is the point of tangency, and so if we go the direction of the y, we're going to increase our dy. Our partial derivative of z with respect to y was root 2 over 4, so it's a positive slope, so we would anticipate going up. Okay. All right, let's go ahead and work on a couple more examples of finding derivatives. So given w is equal to f of x, y, z, let's find the partial w with respect to x, partial w with respect to y, and partial w with respect to z. In A, the problem is w is equal to 3x squared y minus 5xy squared plus 10yz squared. So first we'll find a partial derivative of w with respect to x. So it'd be 6x, and then y is treated as a constant factor. And then minus 5, and then the derivative of the x will be 1. And the y is a constant, so just like the 5, it's still there. And then the 10yz squared is all treated as a constant, so the derivative constant is 0. And so this gives us 6xy minus 5y squared. Okay. If we find the partial derivative of w with respect to y, the 3x squared y will be 3x squared. The derivative of the y will become 1. 3x squared is a constant. Minus, and then it's going to be derivative of the y squared will be 2y, so multiply by the 5 will give you the 10xy. And then plus 10, derivative of the y will become 1, and we'll just have the factors of 10 and z squared. Okay, and lastly, the partial of w with respect to z. So 3x squared y and then the minus 5xy squared do not have the term z in it, so they're both treated as constants. Derivative constants are 0, so 0 minus 0. And then plus, and then the z squared derivative will be 2z times the 10y will give us 20yz, and that'll be 20yz is our partial derivative with respect to z. Okay. All right, we have a few more. Let's look at example B. So we're going to take the derivative of this with respect, the partial derivative with respect to x, y, and z. So partial derivative of w with respect to z. Okay, Now the y minus z in the denominator are treated as a constant, so you could think of it as a 2 in the denominator, so it's just going to be there. You're not going to do anything with it. So it'd be no different than like 5x over 2. What's the derivative of that? 5 over 2. Okay, so likewise this would be 5y over y minus x. The rest are treated as constants. If we take the partial derivative with respect to y, you have variable of y in the numerator and denominator, so we're going to have to use the quotient rule. So it's going to be the low function, y minus z, and the derivative of the top with respect to y would be 5x, minus the top function, which is 5xy, and then times the derivative of the denominator with respect to y, so the y will become 1, and derivative of z with respect to y is going to be 0, and all over the denominator squared. So you're going to have 5xy minus 5xy, so those are going to absorb, and you're going to be left with a negative 5xz, and then divided by y minus z squared. Okay. Now the partial of w with respect to z. Again, you have a z in the denominator, so we could use the quotient rule or maybe a power rule, but let's go ahead and use the quotient rule. So it's going to be the low function, y minus z. Derivative of the numerator with respect to z would be 0 because there's no z's there, minus the top function 5xy times the derivative of the denominator, so the derivative of y with respect to z is going to be 0, and derivative of negative z with respect to z is going to be minus 1, so you just have a minus 1 there, all over the denominator squared. So that's going to give us 5xy all over y minus z quantity squared. Okay, alrighty, let's look at example C. So example C, we have w is equal to x squared, e to the 2y, and then tangent of z. So when we find the partial of w with respect to x, the only thing that we're going to take the derivative of is x squared, which is 2x. The e to the 2y and the tangent of z are constant multipliers, so they'll just be there. Alright, for the next one, the partial of w with respect to y. Now this time the x squared and the tangent of z are constant factors, so they're just going to be there. We're going to take the derivative of e to the 2y, which is going to give you 2e to the 2y. So we'll just put the constant of 2 out in front. Okay, and then finally we're going to take the partial of w with respect to z. So the x squared and the e to the 2y are treated as constant factors, so they're just there. So this is going to be x squared, e to the 2y, and the derivative of tangent is going to be secant squared. So the derivative of tangent of z is secant squared of z. Okay. Alright, so we got just a tiny bit more to go. We're going to look at second partials. Okay. So the second partial derivatives, we can have two different types. Or maybe 4, I guess, depending on how you want to go about this. So second partial derivatives, 2 where you're taking derivative with respect to the same variable. So second partial derivative with respect to x is going to be d squared z over dx squared, which is going to be the partial derivative with respect to x of the partial derivative of f with respect to x. The second partial with respect to y, d squared z over dy squared, is going to be equal to the partial derivative of respect to y of the partial derivative of f with respect to y. Then we have the mixed partials, so the derivative of, partial derivative with respect to x first, then with respect to y would be d dy or df dx, which would be d squared f over dy dx. X first and then y when you're talking about which one do you take the derivative with first. It's going to be x and then y, and then f of and then subscript yx. You're going to take the partial derivative with respect to y first and then take the partial derivative with respect to x. So d dx of df dy is equal to d squared f over dx dy. So we're going to find the mixed partials, fxx, fyy, fxy, and fyx for z is equal to x e to the y plus y e to the x. So we're going to take the partial derivative with respect to x, which is going to be 1 e to the y plus y(e) to the x, which is e to the y plus y(e) to the x. And then we're going to take that and take the partial derivative with respect to x again. And so e to the y will be 0. Its derivative is 0 with respect to x. And then plus y(e) to the x. So that will be y(e) to the x, which will be the second partial derivative with respect to x. Now let's do a mixed partial. So we took the derivative with respect to x. Now we're going to take it with respect to y. So that's going to be e to the y plus 1 times e to the x. And so that's going to be e to the y plus e to the x. Okay. All right, now let's take the partial derivative with respect to y first. So partial derivative of z with respect to y is going to be x e to the y plus 1 times e to the x, which is going to be x e to the y plus e to the x. And now we're going to do our second partials. So the mixed partial, z and then yx, so partial with respect to y first, then with respect to x. And so that's going to be 1 e to the y plus e to the x, which is equal to e to the y plus e to the x. And then we'll do our second partial with respect to y, which is going to be x e to the y, and then derivative of the e to the x with respect to y will be 0. And so that'll give us x e to the y. Okay. So we can observe that our mixed partials are equal to each other, okay? And there is a theorem about mixed partials. And so the theorem states that the equality of mixed partials, f of xy and f of yx, depends on if the mixed partials are continuous on an open disk, okay? And that'll be it for this video. We'll see you next time.